Guys.
Okay, we have to move on. What are we going to do today? Today, we are going to start a new topic, and this new topic is called regression analysis. Called regression analysis. Now,
Regression.
yeah, regression analysis. I'm going to share file with you. Where is the share button here? Right?
Okay.
All right. Um, what is regression analysis in statistics? What is regression analysis? Okay. So for this lecture, we're going to apply regression analysis to estimate linear relationships. Okay. Uh, all along, we have been talking about one variable. Okay, we've been talking about one variable at a time. But here, we are going to look at the relationship between two variables. Now, you can look at two variables, but you're looking at them one at a time. For example, when you compare, say, the average income of, say, female school teachers and male school teachers, but you're looking at one variable, their income, but you're looking at two subpopulations. Okay. So that's a different thing. You're not looking at two variables. You're looking at one variable. You're comparing two populations. That's one variable at a time. Now, but here in regression analysis, we're looking at two variables. For example, income and years of experience. We're looking at one variable is income, and the other variable is years of experience. One variable is number of persons in a household. The other variable is how much they spend on food. That's a variable, okay? Uh, so, but, so now when we look at two variables and look at the relationship between two variables, we take one variable as a dependent variable, and the other variable is an independent variable. For example, when you look at the number of persons in a household and how much they spend on food, the dependent variable would be how much the family spends on food, and how many persons are in the family will become the independent variable. Okay?
Okay.
So how much a family spends on food depends on how many persons they are in the family. All right? So you have a dependent variable. The values of a dependent variable depend on the values of the independent variable.
Okay.
So in regression analysis, we're going to look at number of aspects of this relationship. The relationship could be negative or positive, or maybe there's no relationship if we're trying to explore. Then we look at the size of the relationship. And then we look at how strong the relationship, okay? We look at the negative or positive relationship. Negative or positive. Now, for example, If you look at how much a family spends on food and the number of persons in that family, we ask ourselves, if the more people you have in a family, the more money they spend on food, that is a positive relationship, because the higher the value of the independent variable, the higher the value of the dependent variable. Now think about the relationship between the distance that you travel in your automobile and the amount of gas that is left from the time you started to travel. You will see a negative relationship, because the longer the distance you travel, the less the amount of gasoline will be left in your vehicle. Okay, that's a negative relationship, because as the independent variable goes up, the value of the dependent variable goes down. So that's a negative relationship. Now, the other aspect of this relationship we're going to study is the size of the relationship. Okay? So, for every one person that is in a family, for every one additional person, okay, that's in the family, the expenditure on food will increase by, say, $10 per month or $50 per month. So that is the size of the relationship. The size is when the independent variable increases by 1, then the dependent variable changes by so much, maybe by 5, maybe by 6. That is the size of the relationship. Okay?
Okay.
Right. Now, how strong is the relationship? Now, that is measured by the percentage of changes in the dependent variable that is explained by changes in the independent variable. Okay? For example, when you think about how much gasoline that your vehicle spends for each mile that you travel, okay? So for each mile that you travel, your gasoline decreases by 2 pints. Okay, the gasoline decreases by 2 pints. So that's a -2 in the relationship between gasoline and distance travel. But maybe when you think about me traveling and you traveling and any other person traveling, it might just be that depending on the road, depending on the traffic, the percentage of changes that the percentage of changes in the dependent variable that's explained by changes in the independent variable will be about 90%. So it's not just the distance alone that explains changes in the dependent variable. It could be the condition of the road. It could be also the condition of traffic on the road. Okay? So these are the things we are going to look at. All right. And in order to study this relationship, we use the equation of a line. Okay? So we specify an equation like y is equal to a plus b times x. Okay?
Okay.
A is a constant value. For example, if you think about the gasoline and distance problem, the constant value is that you start with so much gasoline. You start with 12 gallons of gasoline. Okay? So that's a constant value. Now, B is the slope or the rate of change. When X changes by 1, Y changes by B. All right? For example, Y is equal to 10 plus 5X. That's a positive relationship. Okay? If X is equal to 3, Y is equal to 10 plus 5 times 3. Okay?
Okay.
Right? Y is equal to 10 plus 5x. So when x is 3, then 10 plus 5 times 3, then y will be 25. Now, suppose you have a negative relationship, okay? And y is equal to 25 minus 2x, which is negative. So when x is 3, then y is 25 minus 2 times 3, which is equal to 19. All right.
Okay, wait. So just to clarify, basically, so so when when x changes by 1, y changes by b. So that means that if x becomes 4, that would make y into 25 minus what? Minus 8, which would be
Which will be
13.
17. Which will be
Yeah.
17. It will be 17 because 2 times 4 is 8. Is that correct?
Oh, yeah,
So
right. My
20,
bad.
28,
Sorry.
25 minus 8 will be 17.
Okay, got it. Just wanted to clarify.
Yeah. All right. This is what I just explained to you. Um, these are examples. Assuming a linear relationship between the size of a home measured in square feet and the cost of heat, the cost to heat the home in January. How does the cost vary relative to the size of the home? All right.
Mhm.
Okay. In a study of automobile fuel efficiency, assuming a linear relationship between miles per gallon and the weight of a car, how does fuel efficiency vary relative to the weight of a car? Okay. This is one example I like to use because I was traveling from Fargo, North Dakota to Pennsylvania, and I had a U-Haul truck hitched to my car. So usually my car would travel 270 miles on a full tank. So here I started to drive, and after about 145 miles, I would need to fill the gas again. Hey, what's going on here? Maybe my gas tank is leaking. So I go under the gas tank. I go under the car to see if there's any leak in the gas tank. I don't see any leak. Then I fill up the tank again. After 145 miles, I had to fill the tank again. So what's going on here? What's going on here? So I drove by to a mechanic shop and I asked the guy, could you please help me check my gasoline tank? Is it leaking? He said, you know what? I'm just going to be nice to you. I'm not going to charge you for checking your car for you. I'll charge you $10, $15 for it. He said, you have a U-Haul truck hitched to your car, which makes it heavier than without the hitch. I said, oh, that is true. Aha. So that's a very good example about relationship. Okay.
Okay, got it.
The heavier the car, the less fuel efficient. Is that correct?
Got it.
All right. So here is, now the thing in it is when we go back, let's go back. All right.
Okay.
Let's look at this relationship here. If y is 3 for the positive relationship, if y is 3, I'm sorry, if x is 3, y is 25. If x is 4, y is 10 plus 20, which is 30. If y is 5, then, if x is 5, then y is 10 plus 5 times 5, which is 10 plus 25, which will be 10 plus 25 is 35. Now, we can calculate y perfectly if we know x. This is the understandable equation of a line, all right? This is easy to understand because the relationship between y and x is perfect. Now, what happens in regression analysis is that we are now dealing with imperfect data. We are dealing with imperfect data. Let us take the example of the amount of gasoline that is reduced for each mile that you travel. I said that the conditions of the road, the condition of traffic, okay, they all affect the relationship between y and x. They affect the size of B for each person. So in regression analysis, we are dealing with what we call probabilistic data, okay? And so when we specify the equation of a line, we have y is equal to a plus bx plus e. That's an error because it's not always that b is going to be exactly 3. B might be 3 for you and 3.1 for me and 3.2 for somebody else, or it might be 2.9 or 2.85 for somebody else. But on the average, it will be 3, okay? So regression analysis, we call x the independent variable, okay? And E is error due to random effects on known variables or factors, all right? Unknown variables or factors. All right. So regression analysis, our objective is to estimate A, using what we call A hat, because A hat is an estimate of A, because we don't have a perfect relationship. And we estimate B using B hat, because B becomes an estimate of B because we do not have perfect data. For example, so what you get is what we call a tendency. Here is an example, okay? You look at salespeople. Look at salespeople who are selling, say, copiers, okay? They're selling copiers. And you know, to be able to sell copiers to customers, the salesperson needs to make some effort. Am I correct? Okay. They have to make effort, and that effort is measured in calls. They call people and say, we are selling copiers. Okay. Would you like to buy a copier? And somebody says, can you explain to me how the copier works and why I should buy one? So now, so for each salesperson, the number of copiers that they sell will depend on the number of calls. And you know, your ability as a salesperson to sell a copier depends on whether the person you are calling would like to own a copier or is considering buying a copier, but also depend on the ability of the potential customer to pay for the copier. So competitive pricing is a factor, but also depend on the personality of the salesperson. If the salesperson is impatient, if the salesperson is rude naturally, or just the tone of their voice, personality. There are also people that have very good, I would say, people listen to them. That's the way that they talk. You know, it might just be a skill, whatever it is, okay, or just their luck. But what you see here in this chart on the right side is you see a tendency, but the relationship is not perfect. Nevertheless, the more calls a salesperson makes, the likelihood is they're going to be able to sell a copier. Okay, the more calls they make, the more copiers they sell. And so what you see is a tendency, but not a perfect relationship. Not a perfect relationship.
Got
Okay?
it.
Not a perfect relationship. So our objective, therefore, in regression analysis, mathematically speaking, is to estimate a line that goes perfectly in the middle of the scatter plots. You see, these dots here are called scatter plots. Okay? Yeah. They are called scatter plots. And so we try to estimate a line that goes perfectly in the middle of those scatter plots. So that is an average. Okay?
Okay.
Now, the method that we use in regression analysis is called ordinary least squares, OLS, ordinary least squares. And how do we do that? We have the number of sales, the number of copiers sold, and the number of calls made. In order to generate this line, this estimate of the line, sales is Y, the dependent variable. The number of calls is X, the independent variable. Okay?
Okay.
Okay, and I'm going to show you the formula.
All right.
All right. So our objective is to estimate A hat and B hat. A hat being the constant. If you make no call at all, okay, if you make zero call, you're going to make some sale anyway. Okay, so salesperson people can come to the shop. Somebody that needs a copier will call to the shop and say, I'm trying to buy a copier. And if you happen to be lucky, you're going to be the salesperson that picks up the phone and say, yeah, we have copiers. We can sell you one, okay? So somebody who makes no call might still be able to sell a copier. All right. Now, to do that, you have to use the formula here. There's a formula here that you can see is the summation of x minus x bar times y minus y bar divided by the summation of x minus x bar squared. So let's go back and look at the data set. So you must calculate x bar, you must calculate y bar. All right.
Okay.
So you calculate x bar is 96, y bar is 45, all right?
Okay.
As you can see here, see y minus y bar, if you calculate the sum of y minus y bar, you get a 0. If you calculate the sum of x minus x bar, you also get a 0. So that means that our calculation of x bar and y bar are correct. All right, so now that you must multiply x for each observation. Let us take y. For each observation of y, you subtract y from y bar. So for example, since y bar is 45, 41 minus 45 is minus 4. And here again, you get a minus 4, but 51 minus 45 is 6. And 60 minus 45 is 15. And you go down the line. You do the same thing for x, okay? And so you multiply y minus y bar times x minus x bar. Here it is 0. But here, y minus y bar times x minus x bar is 224. And you do that down the line, okay? Then you take x minus x bar to the power 2. And so you take each x minus x bar and square it, multiply by itself. And so you get the numbers here. You do the same thing for y minus y bar. Multiply each one by itself, and you get the amounts here. So from there, you apply this formula here, okay? And so here's the solution, okay? You have the formula that we have on that side, and the summation of x minus x bar times y minus y bar, which we have here, and I'm going to go back. Okay, the summation of that is 6672. All right, I have all the summations here. All right, then you apply the formula, and our estimate of B hat, is 0.2606, and our estimate of A hat is 19.98. So if a salesperson makes absolutely no call, they are likely to sell 20 copiers. And for every 4 calls that a salesperson makes, they'll probably sell 1 copy. And I say for every 4 calls, because for each additional call, they're selling 0.26, but you cannot sell 1/4 of a copier. So that means that the salesperson would have to make approximately 4 calls in order to have a chance to sell 1 copier. And so now, today what we have learned is how to estimate the line, okay? What we have done is how to estimate the line. I have an example here where we apply this method to dividend policy. Like, for example, in financial theory, there is a theory that says that if a company pays dividends, then the price per share of that company is likely to go up because they are paying dividends. Okay, so this is an example of that application, and we use the same formula, the same methods to estimate the price of a share using the equation of the line. Now, we said there are 2 things we do in regression analysis, actually 3 things. One is that we try to estimate what? The size of the relationship. Am I correct?
Right.
Okay. The size of the relationship, which is B hat. This is the size of the relationship, okay? And then we also estimate the nature of the relationship, which is it a positive relationship or is it a negative relationship? So the more sales, the more calls a salesperson makes, the more sales they will have. So in this case, the sign of B is positive, and so we have a positive relationship. All right?
All right.
Okay. All right. Then the other thing we said was to estimate how strong the relationship is. How strong the relationship is. That is measured by what we call the coefficient of determination. The coefficient of determination, what percentage of changes in the dependent variable can be explained by changes in the independent variable. Again, there's a formula here which you have already set up the table. So you calculate the formula And so what happens here is that 65% of the changes in the price of a stock of a company is explained by the dividends that they pay. Okay, 65%. That means there's 35% of changes in the stock price that is not explained by the dividends policy of the company. Okay, here is another example. The cost of maintenance for bus. Okay, the cost of maintenance is the dependent variable. The age of the bus is the independent variable. And so we specify a model that A is equal to A plus B times age, plus, of course, an error. All right. And so the older the bus, the more we spend money on the bus. Again, here is um, the example, the data that we use, and we can estimate that. All right. Now, we are now getting into the next stage, and I prefer that we, first of all, understand, digest in our minds without an overload on just the estimation. The next stage is to ask ourselves whether the estimation we are making is really based on statistical outcome. Is it a random thing, or does the independent variable truly affect the dependent variable? Okay. Does the independent variable truly affect the dependent variable? And that is the next thing we are going to learn, which is the test of significance, a test of hypothesis. So I'm going to leave it there for now so that we can digest the other one, okay? The other information that we have. Otherwise, we're going to overload our heads with information. All right, so this is where we are going to leave it for today. And then next time, we will go to hypothesis testing. Are we correct? Are we okay?
Yeah.
Okay. All right. All right. So thank you very much for stopping by. I'm going to post this so that you can reread, go through the lecture again, including the slides that you see here. I'm going to post them again for everybody to see. All right?
Okay.
Okay. Any questions?
No, that's pretty much it. Thank you so much for helping, and happy Thanksgiving.
You too. Enjoy your Thanksgiving. All right?
Okay.
All right. I'll see you next week.